continue with the MOS capacitor. So MOS cap like MOS capacitor in the case, we have studied the different regions of operation like accumulation, depletion, inversion, and strong inversion. And we have also learned the condition for a strong inversion also. In the case of strong inversion, we have a condition like phi s, that is surface potential, will be equal to 2 phi f. And you know what these terms are, what surface potential is and what Fermi potential is. Surface potential is actually the difference between EIB and EFS, whereas Fermi potential is actually the difference between, Fermi potential is actually the difference between EIB and EFS, and surface potential is actually the difference between EIB and EIS. So this was one condition for strong inversion. So while strong inversion happens, what is actually happening? If we are taking the structure of MOS cap like this, we have a metal part at the top, an oxide layer here. The shaded region is actually the oxide layer. This will be the three-dimensional structure of MOS. So you have a metal part, you have an oxide layer, and finally you have a semiconductor part. The third part is semiconductor part. So if we are taking the semiconductor as p-type, the expected carriers over here is the holes, right? So we are going to apply Vg. While the value of Vg is less than 0, what happens is that at the interface of oxide and semiconductor, right? Accumulation on Vg less than 0 means accumulation is happening. So when Vg is given less than 0, okay, at this interface, that is semiconductor oxide interface, you will be having an accumulation of holes. Okay, we'll be having an accumulation of holes at the interface of semiconductor and oxide. Now we are changing the value of Vg, and finally when Vg is increased in a much greater manner, which is very much greater than 0, then we'll have the strong inversion if this condition is satisfied. So when strong inversion happens, what is actually accumulated over the interface? The interface will accumulated when inversion takes place. Accumulation samayathu, we know that holes are being accumulated at the interface of oxide and semiconductor. When strong inversion happens, what is actually accumulated near the interface? Which is the charge carrier that is accumulated? It's actually called inversion, which is the charge carrier? Is the charge carrier interface joining point? Yes, electrons. Electrons are getting accumulated near the interface, semiconductor and oxide interface. E line that. Okay, electrons will get accumulated at this interface. So this is actually one important property. The property on MOS cap. The most important property of MOS cap, which is made useful in MOSFET, is this property, that is inversion property. That is, we could create a channel of electrons. A p-type semiconductor use it, but still we could create a channel of electrons at the interface of oxide and semiconductor. MOS in the oxide semiconductor interface, we could create a channel of electrons, that is inversion. That is what we call as inversion. Channel of electrons at the interface of oxide and semiconductor. Either condition when strong inversion is being provided. That is when very greater Vg value is being provided. And now we should understand a term called threshold voltage. Very important. Last time also this was been asked, and the derivation for threshold voltage is also asked last time. Was also asked. So threshold voltage is actually the voltage. The only term that we know about voltage is Vg, right? So the voltage at which this strong inversion starts, the voltage, that is the gate voltage at which the strong inversion starts, is actually called the threshold voltage. Normally Vg in a positive value. So at which point of Vg does the inversion starts? The strong inversion start in the Vg value. Vg value we call it as threshold voltage. Okay, note that sentence. The gate voltage at which the strong inversion starts is called threshold voltage. The gate voltage at which the strong inversion starts in a MOS cap is called threshold voltage. So, you can note the point. voltage required to introduce strong inversion. Required to introduce strong inversion. Every strong inversion in semiconductor. In semiconductor is called threshold voltage. And what happens when threshold voltage is being provided? You will get a layer of, you will get an N layer, that is negative layer, അല്ലെങ്കിൽ electron layer. You will get, ഏത് കേസിലാണ്, ഈ കേസിൽ മാത്രം മെറ്റൽ ഓക്സൈഡ് പി ടൈപ്പ് സെമികണ്ടക്ടർ ആണെങ്കിൽ you will be getting a conducting N layer, a conducting N layer, hope you can read this, is induced below gate. This is actually the gate region. Okay, the metal region ആണ് gate region. Gate region താഴെ, that is at this level, oxide semiconductor interface, a conducting N layer is been formed upon when inversion happens. These two things you need to write if you're asked for the definition of threshold voltage. That is, voltage required to introduce strong inversion in semiconductor is called threshold voltage. And under this condition, a conducting N layer is induced below the gate region. This is actually the gate region. The top layer region on a gate region, then you have the oxide layer, and then you have the semiconductor. So below this gate region, actually this N layer, that is the electron layer, is being formed. That is at this interface. Now we need to make a derivation for this VTH. In module, just two derivations are there in this module. ബാക്കിയെല്ലാം നിങ്ങൾക്ക് എഴുതാനും വരയ്ക്കാനും ഉള്ള കാര്യങ്ങളാണ്. But these two derivations are very important when this module is concerned. That is the threshold voltage derivation. So now we need to understand what or how we get into this threshold voltage. That is, we represent it by VTH. This is actually the representation of threshold voltage. And threshold voltage is nothing but the gate voltage itself. നമ്മൾ അപ്ലൈ ചെയ്യുന്ന ഗേറ്റ് വോൾട്ടേജ് തന്നെയാണ്. നമ്മൾ അപ്ലൈ ചെയ്യുന്ന ഏത് ഗേറ്റ് വോൾട്ടേജിലാണ് സ്ട്രോങ് ഇൻവേർഷൻ ഓൺസെറ്റ് ചെയ്യുന്നത്, that particular voltage, gate voltage, is actually called the threshold voltage. So it can be written as VTH is equal to this particular gate voltage is being dropped across the oxide layer and across the semiconductor. Okay, രണ്ട് ഡ്രോപ്സ് ആണ് ഇവിടെ ഉണ്ടാകുന്നത്. പൊട്ടൻഷ്യൽ ഈ അപ്ലൈ ചെയ്യുന്ന വോൾട്ടേജിൽ നിന്ന് തന്നെ നമുക്ക് ഡ്രോപ്പ് ഉണ്ടാകുന്ന ഒന്ന് ഓക്സൈഡ് ലെയറിൽ വിൽ ബി ഹാവിംഗ് എ ഡ്രോപ്പ്, and then across the semiconductor also will be having a drop. Oxide layer drop is actually represented as VOX. നമ്മൾ അപ്ലൈ ചെയ്യുന്ന വോൾട്ടേജിൽ തന്നെയാണ് ഈ രണ്ട് ഡ്രോപ്പ്. VOX, that is oxide layer, plus phi S, that is the surface potential of the semiconductor. These two are the voltage included or voltage drops in this material. One is the VOX, that is oxide layer, the potential that is been dropped across the oxide layer. Then you have the surface potential, is of semiconductor. So you can write VTH, that is threshold voltage, is equal to VOX plus phi S, that is surface potential. And VOX, I will make VOX is actually oxide layer, like VOX, that is about oxide layer. You know about voltage capacitance relation നിങ്ങൾക്ക് അറിയായിരിക്കുമല്ലോ already. You'll be knowing about the voltage capacitance relation. Q is equal to CV, right? You might have learned about this. Q is equal to CV. There is an expression like this. So from that we need to derive the VOX value. Minus QS divided by COX. From this, okay, we are taking minus because the N layer is being formed. So we take it as minus QS divided by COX. You might have learned about this expression, right? Q is equal to CV. അതിൽ നിന്നാണ് നമ്മൾ VOX. This is actually applicable in capacitance. Q is equal to CV. Today we are having a capacitance, like we are having a capacitance of oxide layer. That's why we are taking this expression. Minus is taken since we are having a negative formation also, negative layer formation. So we take it as minus QS plus COX plus phi S. Phi S can be taken as, since we have mentioned that threshold voltage happens at Threshold voltage is the voltage that introduces strong inversion. Strong inversion offer the voltage on threshold voltage. So we can take or substitute phi s with 2 phi f. This is the condition for strong inversion, right? So you will substitute phi s plus 2 phi f. Phi s will be substituted as 2 phi f. So once next sentence you can write next line at onset of strong inversion. At onset of strong inversion, how the equation changes. VTH can be written as VTH is equal to this QS. I am taking it as QD itself because when strong inversion, if you take the figure, energy band diagram figure, you can understand that strong inversion we are having a depletion layer, right? I hope you remember the figure. EFM is there, then you have the oxide layer, then you have the depletion layer. Our depletion layer strong inversion form change. So I am taking this. Okay. So depletion layer is also there. So I am taking it as QDM minus QD, depletion layer, minus QD divided by COX plus 2 phi F. Minus QD by COX plus 2 phi F. Now I need to find the expression for QD. That's the next thing. QD. That is a charge in the depletion region. That is what we need to find. Charge can be written as, since we have already mentioned that we are considering a p-type semiconductor, we can take it as total charge. Define that is a charge density minus Q into Na. Since p-type in the case, here we are not having Pn illa p-type matra. So here in this p-type depletion region, which will be the charge, which immobile charge ions, whether it will be negative immobile ions or positive immobile ions. P-type in the case, whether you are having positive immobile ions or negative immobile ions. This depletion region positive ion or negative ions are not. PN junction in the case, respond. PN junction number depletion region, dotted lines in we are having P side whether we are having negative ions or positive ions. Figure yes, negative ions are here we are having holes. Holes on a P side. Electrons holes accept they will become negative ions every depletion region. So that's why I'm taking it as minus QNA. Minus QNA is actually the charge density, then it has to be multiplied by W, that is the distance, depletion region distance. Here we are not taking ND. We need not consider the N side. N side depletion width consider because we are not having a PN junction. P side we are not having the N side. So everything that we take, we just need to ignore ND term. Expressions we need to ignore the ND term. So QD is equal to minus QNA into W. We usually represent in NA, it's actually per centimeter cube. Charge per centimeter cube. I have already explained this before, I think. We need the total charge in the depletion region. Okay, depletion region and total charge. Depletion region charge density is given as, the unit of Na, charge per centimeter cube. If you need the total charge, you need to multiply this with volume. Is that clear? This centimeter cube cancel total charge. So for that, you need to multiply this with volume. Volume multiply you need to multiply with area and length. Length is W. That is the depletion region width. Okay, then it will cancel and you will get the charge. So I am taking, in all my cases, I will be taking the A value, that is area of cross section, as 1. I will be taking the area of cross section as 1. So I need not write that again. So by just multiplying charge per centimeter cube, charge per centimeter cube, that is charge density. By multiplying the charge density with this Wm value, we will get the value of total charge. we are ignoring the A value, that is area of cross section here. Our area of cross section is taken as 1 throughout this derivation. Clear? Is that clear? We have the charge density, that is charge per centimeter cube over here. Now to get the total charge value, we will be multiplying this with A into Wm, that is the volume. Okay, A into Wm. This A is actually taken as 1. That's why we need not consider this. We will just multiply the term with Wm. Minus QNA. Usually we will minus QNA into A into Wm. But here we are considering A as 1. That's why we are taking it as minus QNA into Wm. That will be QD. And Wm, usually the W naught expression, that is width of the depletion region, the general expression that root of two epsilon V naught. We can write this 2 epsilon V naught by Q into 1 by Na plus 1 by Nd. This is the general expression for width of the depletion layer. This you can write in your equation book also. Okay, equation book. We have few expressions from module 3. Other expression on W naught is equal to root of 2 epsilon V naught by Q into 1 by Na plus 1 by Nd. This is the general expression for depletion region width W naught. Okay. So here in this case, this is actually V0. നമുക്ക് replace ചെയ്യാനുള്ള കാര്യങ്ങൾ നോക്കാം. നമ്മുടെ ഈ കേസിലേക്ക് നമ്മുടെ മോസ്ഫെറ്റിന്റെ കേസിലേക്ക് വരുമ്പോൾ how it will change, that is what we are going to see. This V0 will be changed as phi S. Okay, phi S ആവും V0 എന്ന് പറയുന്നത്. And this ND term will go because we are not having a N region. We are not having an N region. We are just having the P region. That's why ND term. ഈ ND term നമുക്ക് ignore ചെയ്യാം. So the things that will be left will be, this is further equal to minus QNA into, instead of WM I will be writing root of 2 epsilon. Instead of V0 we have phi S. That semiconductor potential is phi S, that is surface potential. Instead of V0 you can write phi S divided by QNA. We are ignoring the ND term. For instead of phi S, you can substitute 2 phi F minus QNA root of, actually this root is for the entire term. Okay, 2 epsilon into 2 phi F divided by QNA is equal to, how will this expression turn out to be? How will this change? Please find. Okay. What happens to QNA term? Then the final answer, you just tell me the final answer. Final Q&A, ഈ Q&A റൂട്ടിനകത്താണ്. എങ്ങനെയോ ഇതിനെ ക്യാൻസൽ ചെയ്യണമെങ്കിൽ യു നീഡ് ടു ടേക്ക് ദിസ് ടേം ഇൻസൈഡ് അല്ലെ. ഈ Q&A ടേം കൂടെ അകത്തോട്ട് കൊണ്ടുപോകണമെങ്കിൽ യു ക്യാൻ ക്യാൻസൽ ദിസ്. ഈ Q&A അകത്തേക്ക് കൊണ്ടുവരണമെങ്കിൽ വി നീഡ് ടു സ്ക്വയർ ദാറ്റ് അല്ലെ. You need to square this term and take this inside, and then you can cancel one Q&A. പിന്നെ റിമൈനിങ് എന്തായിരിക്കും വരിക എന്ന് പറഞ്ഞാൽ I just need the final answer. പെട്ടെന്ന് എനിവൺ ആർക്കെങ്കിലും കിട്ടിയോ? ഒന്നുമില്ല. ഈ Q&A you need to cancel with this, so you need to take this Q&A term into this square root. In order to take this inside you need to take the square അല്ലെ. Q&A the whole square അകത്തേക്ക് കൊണ്ടുപോകണം. Then you can cancel one Q&A term. The remaining term you can write. Just tell me whether I am writing right or not. Minus 2 root of epsilon Q N A by F. Whether this is correct or not. Have you got this value? എങ്ങനെ വന്നെന്ന് മനസ്സിലായോ? 2 into 2 to 4. So 2 you can take outside. 4ന്റെ റൂട്ട് എന്ന് പറയുന്നത്. ക്ലിയർ ആണോ ഇത് എങ്ങനെ വന്നെന്നുള്ളത്? വൺസ് ഇത് പറഞ്ഞു കഴിഞ്ഞാൽ I will repeat this. No issues. Okay. So this is the expression of QD. QD മാത്രമേ ആയിട്ടുള്ളൂ ഇപ്പോൾ. QD is actually the charge value. We have the charge density. From charge density, if we need to get the charge, we need to multiply charge density with volume. Volume എന്ന് വെച്ചാൽ area into length. Area we are taking it as 1, so you will multiply just it with the length. That is the depletion region width. Length in this case is depletion region width. Yeah, you have taken the expression for depletion region as this one. Okay, this is the general expression, and instead of V0 we need to substitute phi s, because we are considering the p-type semiconductor with surface potential phi s. Most capacitor cases we are not having V0, we are having just phi s surface potential, and then you get the value like this. Now you just need to substitute the value over here. You just need to substitute it over here, and you will get is equal to minus QD is actually okay. So 2 minus will be there. 1 minus this minus will go, since we are having already a minus over here. This minus will go. It will be 2 root of epsilon Q N A by F divided by COX plus 2 by F. അധികം ലെങ്ത് ഉള്ള ഡെറിവേഷൻ അല്ല, but this was asked last time. I think it's for 8 marks or something. This derivation, ഈ derivation മാത്രം. Each step will be having mark. Each step. So ഇവിടെ നിങ്ങൾക്ക് പ്രത്യേകിച്ച് ഒന്നും ആലോചിക്കാനില്ല. You have just the basic idea, that is this applied voltage is dropped across the oxide layer and the semiconductor. VG, that is applied voltage, is dropped across the oxide layer and the semiconductor. So this VG is actually what we call threshold voltage when this condition is satisfied. So we are taking VTH is equal to VOX, oxide layer drop, plus the surface potential drop, that is the semiconductor drop. So oxide layer voltage is taken as, since oxide layer is acting as a capacitance, we can take its equation as minus QS by COX, since we are having a negative layer over there, minus QS by COX, plus 2 phi F. Phi S ine namukku 2 phi F nu vilikam, since it is strong inversion. Threshold voltage usually happens at strong inversion. That's why we are replacing phi s with 2 phi f. Then all the remaining things are been done already. This is also very important from the examination point of view. This expression you can write in the equation book, equation paper. VTH is equal to completed. Okay. Can I rub this off? കഴിഞ്ഞല്ലേ? Okay. So I will just take you through another topic which is in relation with this topic. ഇതുമായിട്ട് ബന്ധമുള്ളതാണ്. In other words, you can say why we were actually focusing on this Mosfet. Mosfet, I have already mentioned that one of the important property of Mosfet, which is been utilized in Mosfet, is the strong inversion condition. Strong inversion condition എന്തായിരുന്നു? നമ്മൾ gate voltage apply ചെയ്യുമ്പോൾ below the gate region, we are actually forming a negative layer or n layer. We are actually forming a n layer in a p-type semiconductor. With p-type semiconductor, we are actually forming an n layer by providing a higher gate voltage or providing a threshold voltage. So that is required in this case. In the case MOSFET in the case. Have you learned about MOSFET? Have you heard about MOSFET? MOSFET kettundo? Which are the different terminals of MOSFET? Have you heard of MOSFET? Metal oxide semiconductor field effect transistor. That is MOSFET. Metal oxide semiconductor, that is MOS, metal oxide semiconductor field effect transistor. Okay, that is MOSFET. I'm actually going to draw the structure of MOSFET. So you have a P substrate. Okay, so this will be two regions. N plus means heavily doped. N plus means heavily doped N regions. If I am indicating plus sign, that means that particular region is heavily doped. I have an oxide layer. G. Source, gate, drain. Have you heard about these terms? Source, drain. I need to explain this again. Have you heard of these terms at least? Source, drain, gate. Hello? Formula, fine. So, MOSFET, in the case, we have already learned about BJT, bipolar junction transistor, where we had the three terminals called emitter, base, and collector. Okay, that was what bipolar junction transistor or BJT is. The applications, modes of operation, we have the active mode of operation, saturation mode, and modes of operation. We have some applications like it will be working as an amplifier or it will be working as a switch. Switch means on-off conditions will be provided. That is logic 1 or logic 0 will be provided. So, in applications, BJT, bipolar junction transistor, where we had emitter, base, and collector as the terminals. In case of MOSFET, we are having, it's again a 3-terminal or 4-terminal, you can say, because we will be having a 4th terminal called body terminal or B terminal. So main terminals are source, gate, and drain. Here, if you closely observe, you can see we have the metal oxide semiconductor. MOS, that is the metal part, this one. Metal part is there. This shaded region is the oxide part, and then you have the semiconductor, P-type semiconductor. A structure you just ignore these two end regions. The end regions, you are having a metal part, this one metal, this oxide layer, and finally you have the big P-type semiconductor. That is M oxide layer, MOS, metal oxide semiconductor. Okay, metal oxide semiconductor concept, we are using that in the MOSFET. We have the metal oxide and then the semiconductor. So you tell me, I have two N plus regions included or induced in this P substrate. In P substrate, I have induced two N plus regions. Okay, and these two regions, regions, I have induced N plus or heavily doped these two regions with N or negative charges. So I have a source N plus region and a drain N plus region. Now I need to have a flow of electrons from source to drain. This source in the drain lake, if I need to make a transition of electrons from the source to drain, what I need is a channel over here. This is actually a P-type region. The P-type region matron. Okay, there is no channel for the charge particles in the source to reach the drain. And this source in the drain lake, I need a channel over here. For that, what should I do? Simpler example, you have a tap. You have a tap over here. You have some container. Under. Okay. Tap in you have. Okay. If you need this can be considered as source. This can be considered as drain. This is actually the condition. So now, if you need to have the water flow, you need to turn on this, right? This gate, you need to open this one. You will be having a water flow through this, and it will reach the drain. In a similar manner, you need to have a channel between these two regions. That is, in between source and drain, you need to have a channel, and that channel can be created only with the help of gate voltage. What was our condition of strong inversion? Strong inversion, that is when we are applying a very large value of gate voltage, region, what will be formed? Tell me that. We have a metal oxide semiconductor, MOS. MOS in the case, strong inversion. What will be formed at this portion? What will be formed at this portion? And that is formed here. If I am doing the strong inversion, what will be formed at this region? E interface and that is formed here. Yes, very good. We'll be having, when we are having a metal oxide semiconductor, electrons from the source to drain. Flow current. We need to have current in the circuit. For that, you need to have flow of electrons. So you need to have a flow of electrons over here. You need to have a channel over here. That channel will be created when the gate voltage is applied for strong inversion. Strong inversion like form you will be getting a channel of electrons. In the strong inversion. Is that clear? Hello? Okay. We are having a piece of MOS concept. This is M, metal region. This is your oxide region. This is your P region. നമുക്ക് MOS നമ്മൾ VGS less than 0 apply ചെയ്യുമ്പോൾ accumulation ആയിരുന്നു. Greater than 0 apply ചെയ്യുമ്പോൾ you have depletion, inversion and strong inversion. അതിൽ strong inversion എന്ന് പറയുന്ന കണ്ടീഷനാണ് നമുക്ക് ഇവിടെ വേണ്ടത്. Because നമുക്ക് ഇവിടെ രണ്ട് N+ regions. One is source and another is drain. You need to have flow of electrons between these two regions. അത് വേണമെങ്കിൽ ഇത് ആക്ച്വലി P region ആണ്. ബട്ട് ഇവിടെ ഒരു N region അല്ലെങ്കിൽ ഒരു N ചാനൽ ഉണ്ടായാൽ മാത്രമേ എന്ത് സംഭവിക്കുള്ളൂ? You will have a flow of electrons through this region. അല്ലെ? എങ്കിൽ മാത്രമേ നമുക്ക് കറണ്ട് ഉണ്ടാവും. So in order to have a negative layer over here, എന്താ നിങ്ങൾക്ക് ചെയ്യാൻ പറ്റുന്നത്? ഇവിടെ ഈ പൈപ്പ് ഈ ഗേറ്റ് ഈ ഒരു വാൽവ് തുറക്കുന്നത് പോലെ തന്നെ you need to apply a gate voltage that is equivalent to VTH. VTH എന്ന് പറയുന്ന ഒരു threshold voltage apply ചെയ്യുമ്പോൾ you will form negative layer of electrons here. ഒരു നെഗറ്റീവ് ലെയർ ഇവിടെ ഫോം ചെയ്യും, അല്ലെങ്കിൽ N ലെയർ ഫോം ചെയ്യും. അതാണല്ലോ സ്ട്രോങ് ഇൻവേർഷൻ. സ്ട്രോങ് ഇൻവേർഷന്റെ ബാൻഡ് ഡയഗ്രം നിങ്ങൾ ഓർക്കുന്നില്ല? There was an accumulation of electrons near the interface. അതുപോലെ you will be having a negative layer over here. Then what happens? Then you have actually having a channel. ഒരു ചാനൽ നിങ്ങൾക്ക് കിട്ടി. ആ ചാനലിൽ കൂടെ സോഴ്സിൽ നിന്ന് ഡ്രെയിനിലേക്ക് carriers can move and you will have a current in the external circuit. Clear ആണോ? Is that clear? ഇനി ഒരു കാര്യം ഞാൻ പറയാം. ഇതിപ്പം ഇനീഷ്യലി there was no channel over there, അല്ലെ? ഇനീഷ്യലി നമുക്ക് ഇവിടെ ചാനൽ ഉണ്ടായിരുന്നില്ല. This was the condition initially. You were not having a channel here. So ഇങ്ങനെയാണ് കേസ് എങ്കിൽ you will have a type of MOSFET called Enhancement Mosfet. എന്ന് വെച്ചാൽ initially this will be in the off condition. Initially off condition ആണ്. Initially you are not having a channel in between the source and drain. Then it is called Enhancement Mosfet. That will be initially in the off state. By applying gate voltage, this will turn into on state. അപ്പോൾ enhancement MOSFET എന്ന് പറയുന്നത് initially off conditionലായിരിക്കും. That can be turned on only by applying a greater VG. VG apply ചെയ്യുമ്പോൾ you will form a negative layer. Then they will be having current through the circuit. That is actually called enhancement MOSFET. There is another type called depletion MOSFET. Depletion MOSFET ഇതിന്റെ നേരെ ഓപ്പോസിറ്റ് ആണ് കേസ്. That will be initially in the on state. Initially on state എന്ന് വെച്ചാൽ initially itself there will be channel over here. നമുക്ക് ഇവിടെ ചാനൽ ഉണ്ടാവും. തുടക്കത്തിൽ തന്നെ we will be having channel. That is, it will be initially in the on state. We can turn off the device. Turn off എങ്ങനെ ചെയ്യും? ഈ ഗേറ്റ് വോൾട്ടേജ് കുറച്ചാൽ ടേൺ ഓഫ് ആവും. ഗേറ്റ് വോൾട്ടേജ് കുറയ്ക്കുന്ന സമയത്ത് through source and drain. Clear? That will be initially in the on state. ഏതാണ് depletion mode takes that will be initially on state. Can turn off സമയമാണ് strong inversion form ചെയ്യുന്നത്. When it is been reduced, initially on state ലാണ് we can turn off that device, then it's called a depletion MOSFET. Thus there are two types of MOSFETs, enhancement MOSFET and depletion MOSFET. Okay. So ഇപ്പൊ നിങ്ങൾക്ക് മനസ്സിലായിട്ടാവും നമ്മൾ എന്തുകൊണ്ടാണ് ഈ MOS മെറ്റൽ ഓക്സൈഡ് സെമി കണ്ടക്ടർ പഠിച്ചത്. മെറ്റൽ ഓക്സൈഡ് സെമി കണ്ടക്ടറിന്റെ ഇൻവേർഷൻ, സ്ട്രോങ് ഇൻവേർഷൻ എന്ന് പറയുന്ന കണ്ടീഷൻ നമുക്ക് ഇവിടെ ആവശ്യം വന്നു. In order to have a channel between the source and drain. സോഴ്സിനും ഡ്രെയിനും ഇടയ്ക്ക് ഒരു ചാനൽ ഫോം ചെയ്യാൻ വേണ്ടി we have made use of strong inversion condition of MOS. MOSലെ strong inversion condition നമ്മൾ ഇവിടെ യൂസ് ചെയ്തു in order to have a channel between source and drain. Clear? Is that clear? Okay. So you can mark your attendance. Correct 9:50 തന്നെ you need to join. Okay. നിങ്ങൾ ആ ലിങ്ക് ഓൾറെഡി നിങ്ങളുടെ ഗ്രൂപ്പിൽ വന്നിട്ടുണ്ട്. ആ ലിങ്കിൽ ജോയിൻ ചെയ്യുക, ഫോഴ്സിൻ്റെത്. അത് കംപ്ലീറ്റ്ലി പാർട്ടിസിപ്പേറ്റ് ചെയ്താൽ മാത്രമേ നിങ്ങൾക്ക് ആക്ടിവിറ്റി പോയിന്റ്സും അതുപോലെ you will be getting your certificate.